Those cells have really proven their worth in terms of like energy density and capability, and I really think we're only in the beginning of that.
Until now, we have good reason to be concerned. Will electric cars go the distance? Will they charge quickly enough? Will the batteries last? Will they be affordable? Today, electric car batteries remain the main source of skepticism and the biggest barrier to widespread adoption. Not all EVs offer a range of over 300 miles. Fast charging can still take up to 30 minutes, and many drivers are deterred by the fear of battery degradation, losing more than 25% capacity after just a few years. To make matters more complicated, most EVs in the US are still proving themselves in the market, while Chinese electric car companies are expanding rapidly. However, Tesla is developing a next-generation battery system that's advancing faster than almost any technology we've seen. Each year, the range increases by 35%, charging time drops to just 5.9 minutes, manufacturing costs fall to $97 per kilowatt hour, and thanks to new materials, battery lifespan is nearing the 30-year mark. Car makers, from Ford and GM to Hyundai, are watching closely, pouring tens of billions of dollars into this breakthrough. So, what kind of insane battery is Tesla developing? And when will these new batteries hit the road? Welcome to Tesla Car World. If you find this Tesla update interesting, please like it. This will tell YouTube to share more of this information with you and more tech fans. Thanks.
That's going to continue to happen. That doesn't mean we don't also look at trends like solid-state batteries and supercaps and other things that might provide other alternatives of energy. But
So yes, major players like Mercedes-Benz are going all in on solid-state batteries. Chery is joining the race, and a wave of other companies are scrambling to catch up, treating this tech like a golden ticket to the future of electric vehicles. From the outside, it may seem like Tesla is sitting this one out, doing nothing. But that's exactly the perfect misdirection. While the rest of the industry is loudly chasing solid-state batteries, Tesla has been quietly upgrading its own battery technology, and it's happening right in front of us without many noticing. The truth? Tesla batteries aren't just getting better year after year. They're charging faster, performing stronger, and most importantly, they're getting cheaper. And, in the words of Lars Moravy, Tesla's vice president of vehicle engineering,
if you look year over year, battery improvements have always been incremental. About 3% energy density improvement year over year, or something like that. And
so here's the thing. If we can keep increasing energy density, improving charging speed, and dropping the cost of EV batteries, then what are we even arguing about anymore? We mean, just look at Tesla. Their battery prices have plummeted in a way that's honestly kind of insane. Back in 2013, Tesla was paying over $800 per kilowatt hour. Today, it's down to about $110 per kilowatt hour. And by 2026, they're aiming for just $97 per kilowatt hour. That's cheaper than LFP batteries, the very chemistry that's been bragging about low costs for years. Now, people love to say, EVs are too expensive, they don't charge fast enough, and they don't go far enough. But here's the kicker. All of those arguments are falling apart year after year. Let's take range, for example. It keeps going up. Like, seriously. You remember the Tesla Model Y, right? The all-wheel drive version earlier this year had a range of about 530 kilometers. Then Tesla quietly updated it, and boom, 550 kilometers. Fast forward a few months, and guess what? 600 kilometers. No big announcement, no flashy marketing, they just made it better. And that's not even the rear-wheel drive version. That one? It's had a 600 kilometers range for quite some time already, with a smaller, cheaper battery pack. So, what's your prediction for Tesla Model Y battery cost? Drop your thoughts in the comments. We'll reply to the top ones. So what we're actually seeing here is a pattern. Electric vehicles are getting better and cheaper every year. And the biggest driver behind that? Battery technology. Prices are falling. Energy density is going up. Charging speeds are improving. And Tesla is leading that charge. Pun absolutely intended. Which brings us to the big question. Do we really need solid-state batteries? Sure, they'd be cool. Faster charging, higher energy density, maybe even lighter packs. But let's be real. Lithium-ion and lithium iron phosphate batteries are already proving they're more than enough for 99% of drivers. They're working now. They're scaling now. They're getting cheaper now.
Yeah, I mean, battery tech is definitely at the forefront of a lot of things we do at Tesla. It powers every product that we make.
Basically, lithium iron phosphate batteries are currently the cheapest type of battery in the world. Sodium batteries will likely replace lithium phosphate batteries soon when it comes to energy storage. That's because, although sodium has lower energy density, it still offers some advantages. And one of them is cost. The cost of sodium is extremely low. So that shift is going to happen, right? The low-end segment of the market will probably be dominated by sodium-ion batteries in the next few years. And those electric vehicles will be very, very affordable. They'll be even cheaper than equivalent internal combustion engine vehicles. But Tesla said they still believe there's a lot of progress to be made in microchemistry and in those form factors. And we agree with that. You know, we really have to give Tesla some credit here. Tesla got it right. They were the first company in the world to use lithium iron phosphate batteries in cars. And they didn't just use them in a few vehicles. We mean around 70% of all Teslas were already using lithium iron phosphate batteries years before traditional automakers decided. And here's the crazy part. When Tesla predicted about the battery market, they might have been right from the very beginning. Why? Because while most of the world is still talking about batteries like they're some kind of fixed, unchanging technology, a new wave has quietly been gaining momentum. In just the past 6 months, we've seen something that just a few years ago would have been considered unthinkable. The charging speeds of new EV models have doubled, or in some cases, nearly quadrupled. From 250 kilowatt to 300 kilowatt. That's no longer the ceiling. We're now talking 500, 600, even 1,000 kilowatt ultra-fast charging. But here's the part that really blew our mind. Most of the batteries hitting those insane speeds? They're the same old batteries. Nothing's changed. Literally the same. Same battery structure, same materials, same manufacturing tech. There's only one key difference: the software. That's right. Automakers have finally realized that these batteries can actually handle ultra-high charging speeds. And by tweaking just a few lines of code, they're now able to push massive amounts of current without damaging the battery. And that, right there, is one of the biggest breakthroughs happening right now. We don't need to redesign the physical battery. No new formats, no new materials, no nothing, except a little software intelligence. And it's not just about charging speeds. The overall performance of the car, from driving range to thermal efficiency, has been improving year after year, simply through software updates. So if you still think batteries only get better when the hardware changes, you might be missing one of the most important pieces of the puzzle: software, cooling systems, input current. All of those are quietly changing the game. And here's the real kicker. While performance is going up, battery prices are going down. That's something we've almost never seen before. Production is scaling, costs are dropping, and energy density is still rising. Sounds crazy? But that's the future we're stepping into. And Tesla looks like they've known it all along. When Tesla ramped up production of its 4680 cells at megafactories like Giga Austin and Giga Berlin, it wasn't just a matter of volume. Battery production costs dropped significantly. And the strange part was that energy density actually increased. Back at Battery Day 2020, one of the most iconic tech events of the decade, Tesla didn't just unveil a new 4680 battery cell. They tore up the rulebook and introduced a tabless, significantly larger design that, in Elon Musk's words, would reduce cost per kilowatt hour by up to 56% compared to the older 2170 cells. 56%. That's not a small number. And here's how they made it happen. 14% came from scaling up the size of the cells. 18% came from a more efficient manufacturing process. 5% came from adding silicon to the anode. 12% came from restructuring the cathode. And the final 7%, that came from integrating the cells directly into the vehicle's structural frame, eliminating the need for a bulky battery pack casing altogether. Put it all together, and the result is undeniable. The 4680 isn't just a new battery cell. It's a financial lever that will power Tesla's EV future. And it's not just about cost. The tabless design doesn't just reduce internal resistance, It also allows for higher current flow, improved cooling, and faster charging. All while keeping temperatures lower and increasing battery lifespan. To put that in perspective, the original Model S from 2012 had a range of 265 miles on a full charge. Today, the top-tier version can exceed 415 miles. That's 150 extra miles, purely from better batteries. No engine changes, no extra fuel. And according to Murav, one of Tesla's senior engineers, the company is transitioning many of its production lines to a unified standard block design for battery packs, one that gets updated every few years. On top of that, Tesla has already begun shifting toward next-gen battery cells from CATL and LG, all while continuing to manufacture 4680 at both Giga Nevada and Giga Texas. Additionally, the company also manufactures its own batteries in-house, the high-capacity 4680 batteries for themselves. So when will this affordable battery be used in Tesla's EV? A Chinese EV company has confirmed that their electric vehicle, coming next year, will have a driving range of over 1,000 kilometers thanks to solid-state batteries. But what I find really interesting about this story is, manufacturers have been talking about solid-state batteries for nearly a decade now. Lots of promises, lots of prototypes, but very few have actually revealed the technical structure of these batteries. This time, though, Chang'an, in partnership with Huawei, has disclosed the layout, materials, and even the design specifications of the solid-state battery they plan to put into mass production vehicles. That's rare, and it makes me actually think, well, this might actually be real. They stated that the battery will use a high-nickel cathode, a silicon-carbon anode, and a high-conductivity solid-state electrolyte, combined with a 1,200-volt electrical architecture and a 12C fast charging system. The result is a battery with an energy density of around 400 watt-hour per kilogram, enabling the vehicle to achieve a real-world range of over 1,000 kilometers on a single charge. They also claimed that the fast charging system can reach speeds of up to 1,200 kilowatt, far beyond any commercial vehicle available today. With a motor capable of spinning at 30,000 revolutions per minute, this clearly points to a future-forward technology. However, while many Chinese companies are chasing breakthrough innovations with solid-state batteries, Tesla is taking a different path, developing improved lithium-ion batteries at a sustainable pace with clear manufacturing efficiency. At the July 20, 2025 event, Lars Moravy emphasized that the company continues to refine both LFP and NMC battery lines. According to him, these batteries can still improve their energy density by about 3% per year, thanks to factors like higher nickel cathodes, increased silicon in the anodes, and optimized cell and pack designs. It's not a revolutionary leap like solid-state batteries, but it's a stable, real, and scalable path forward. Tesla has also broken ground on an LFP battery factory in Nevada, which is expected to supply low-cost batteries for US-made Model 3 and Model Y vehicles. This move helps pave the way for the long-promised $25,000 car Elon Musk once teased, while significantly reducing battery costs. According to multiple reports, the production cost for LFP batteries is now dropping below $100 per kilowatt-hour, a price point never seen before. That said, Tesla hasn't completely dismissed solid-state batteries. The company continues to research this technology, along with supercapacitors, but with the view that as long as solid-state batteries haven't proven their scalability, longevity, and stability, lithium-ion remains the core platform. Panasonic, Tesla's major battery partner, even recently stated that it considers solid-state batteries a niche solution, not viable for replacing traditional batteries in mass-market EVs. That's a striking stance, especially when compared to the bold claims coming out of China. We know what you're thinking. Is Tesla falling behind? Not at all. What you need to remember is this. Tesla is still the global leader when it comes to battery technology that's actually being deployed at scale. While the company hasn't announced a 1,000-kilometer battery, the Model S Plaid already delivers over 600 kilometers of range. The Cybertruck uses 4680 cells, which offer faster charging and higher performance than the older 2170 cells. With each new generation, Tesla continues to improve energy density and reduce cost. We're not denying that this could be the future, possibly within the next 5 to 7 years. Solid-state EVs that fully charge in 10 minutes and drive 1,000 kilometers will eventually arrive. But if you ask me which technology is ready for the mass market today, capable of powering millions of vehicles per year, the answer is still Tesla, with its continuously improving lithium-ion batteries leading the way. The future may be bright, but for now, you still need a company grounded in reality to make it happen. Gas-powered cars are bound to disappear at some point. Maybe not tomorrow, maybe not even in the next few years. But yes, once most countries start banning emission-producing vehicles, it's game over. In other words, electric vehicles are what the world is betting on for the long haul, even if right now they're still more expensive than gas-powered ones. The battery can make up nearly 40% of the total cost of an electric vehicle, and currently, most of these batteries use lithium. In fact, about 75% of EVs on the road today run on lithium batteries. But believe it or not, that's about to change. In the not-so-distant future, lithium could be completely replaced, at least in EVs. Why? Because there are tons of new battery technologies being developed around the world, all with one mission: to knock lithium off its throne. Almost no one knows what just happened at Tesla. But what about this new battery? It could completely rewrite the future of the company, and it might just be Elon Musk's biggest gamble yet. These new types of batteries have clearly been in the works at Tesla for quite some time. Although the company has tried to keep things under wraps, internal leaks have made it obvious that Tesla wants the world to know they're working on something big to push EV battery technology forward, especially for the more affordable models set to launch in the near future. What's incredible is that this new battery is made from much more common and much cheaper materials than lithium, yet it delivers 3 times the energy density of today's lithium-ion batteries. Of course, no technology is perfect from the start. There are still a few hurdles to overcome, but overall, this battery already outperforms in nearly every aspect. And once those final challenges are solved, it won't just compete with lithium, it could completely replace it, ending lithium's reign once and for all. And now, real-world results are starting to back up that potential. Reports show the new battery technology Tesla is testing has reached energy densities of over 700 watt-hour per kilogram, a figure strong enough to completely reshape the battery industry. To put that into perspective, if you equipped a Tesla with this battery, it could travel over 700 miles, or roughly 1,126 kilometers, on a single charge. Some estimates even push that number closer to 1,000 miles, about 1,600 kilometers per charge. That's such a massive leap that even the most optimistic EV enthusiasts are having a hard time believing it. And while lithium-ion batteries are still widely used today, as we mentioned earlier, they haven't seen any real breakthroughs in energy density for decades. Do you think the new Tesla 4680 batteries will actually launch under $100? Subscribe now so you don't miss the next breaking Tesla update. It's coming in just 2 days. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. Lithium-ion is everywhere around us. In phones, laptops, and more than 95% of today's EVs still rely entirely on this technology. That number alone is enough to show that lithium-ion remains the gold standard in the battery world, with few competitors capable of replacing it. But the truth is, lithium-ion batteries have been standing still for the past few years. How long has it been since we saw a real leap in performance? Energy density is still stuck at around 250 watt-hours per kilogram. Prices haven't dropped significantly, and the risk of fire or explosion remains a constant concern. This is also why electric vehicles still haven't convinced all consumers. They remain expensive, and safety concerns continue to linger. Recently, EV manufacturers have begun shifting to a newer option, one considered far more efficient than lithium-ion's aging limitations: solid-state batteries. Solid-state batteries aren't just hype. Backed by rapid R&D and billions in investment from giants like BYD, Tesla, Toyota, and QuantumScape. This next-gen tech is already outperforming lithium-ion in energy density, range, and charging speed. Mass production could start as soon as 2026. Could this be the final catalyst for EVs to leave gasoline behind for good? And what sets an EV with solid-state batteries apart? Welcome to Tesla Car World. So, what makes solid-state batteries worth paying attention to? We all know that most new battery technologies still haven't earned the public's full trust, and for good reason. Many are still stuck in the research or testing phase, and bold claims about breakthrough performance often come without real-world proof. But in the middle of all that noise, BYD, one of the world's leading EV and battery tech companies, and a top rival to Elon Musk's Tesla, is making some serious waves. As you may know, BYD is already behind the Blade battery, a lithium iron phosphate battery known for its safety and durability. So reliable, in fact, that Tesla uses it in its Model Y sold in Europe. But now BYD is going even further by developing the very battery the world has been chasing, solid state. They've already built a working prototype on a pilot production line and are expected to begin large-scale installation in their vehicles soon. This new battery boasts double the energy density of current cells, enabling up to 900 miles of range on a single charge. And that charge takes just over 4 minutes. If BYD sticks to its roadmap and delivers as promised, this battery could completely reshape the global EV market within this decade. Solid-state batteries mark a major leap forward in energy storage technology by completely eliminating flammable organic solvents and replacing them with solid materials like ceramics, sulfides, or polymers. This shift allows energy density to reach 400 to 500 watt-hour per kilogram, 2 to 3 times higher than that of traditional lithium-ion batteries. Imagine a suitcase the same size, but now able to hold twice as many clothes. Thermal resistance also sees a huge boost. Solid-state batteries remain stable across a wide temperature range, from -4 degrees Fahrenheit to 212 degrees Fahrenheit, equivalent to -20 degrees Celsius to 100 degrees Celsius, drastically reducing the risk of failure due to extreme heat or cold. Durability? Even more impressive. With no more electrode wear or swelling issues, solid-state batteries can handle 2,000 to 3,000 charge cycles while still retaining over 80% of their performance. That's like doubling the driving distance of a car before it ever needs a major overhaul. It might sound almost too good to be true, but these very advantages are exactly why battery giants around the world are racing towards solid-state technology. In addition, many leading corporations are actively developing and commercializing solid-state battery technology. QuantumScape recently reported a breakthrough in its Cobra project, the successful fabrication of a micrometer-thin ceramic separator, a crucial step, as thinner separators lower interfacial resistance and enable higher current density. This new production method is said to be 25 times more efficient than the previous Raptor generation. The company has also partnered with Volkswagen's PowerCo, targeting a commercialization window between 2026 and 2028, in sync with the rollout of next-gen EV platforms. Solid Power, meanwhile, is focused on sulfide electrolytes, reporting room temperature ionic conductivity of approximately 1 millisiemens per centimeter. While not the theoretical maximum for sulfide systems, it's strong validation of their cell architecture, proven through 1,000 cycle tests on the BMW iX, a notable real-world milestone. On the oxide front, Toyota is developing LLZO, lithium lanthanum zirconium oxide, a solid electrolyte with a high melting point and stable performance from -4 degrees Fahrenheit to 212 degrees Fahrenheit. Their plan to integrate it into Lexus EVs by 2027 shows strong confidence in both its thermal and mechanical durability. As for manufacturing capacity, Ferasis Energy has launched a 0.2 gigawatt-hour pilot sulfide battery line in Germany, aiming to scale up to 1 gigawatt-hour per year by 2026 for both EVs and grid storage. Finally, Huawei has unveiled a hybrid sulfide polymer battery boasting 450 watt-hour per kilogram energy density, over 2,000 kilometers of range, and an 80% charge in just 10 minutes. Impressive figures that, while promising, will need to be validated through rigorous life cycle testing and the demanding conditions of the automotive industry. The truth is, every time a new battery type makes headlines, most people probably just roll their eyes and think, "Oh great, another gimmick." There's a common belief that these new batteries will never make it to mass production, let alone become mainstream in electric vehicles. And, honestly, we used to think the same. That reaction is completely understandable. Lithium-ion has earned its place as the gold standard for EVs thanks to its stable energy density and a dramatic drop in cost. From around $1,000 per kilowatt-hour in 2010 to roughly $130 per kilowatt-hour by 2024. However, take a closer look, and it's not just us. Many experts agree. Lithium-ion is one of the biggest reasons EV performance has hit a ceiling. Despite being widely adopted for decades, this technology has slowed innovation and eroded public confidence in electric vehicles. By key metrics, traditional lithium-ion batteries typically offer around 180 to 250 watt-hour per kilogram. In contrast, next-gen solid-state designs are targeting 400 to 500 watt-hour per kilogram. That kind of jump can translate to either lighter battery packs or significantly longer driving ranges, without increasing size or weight. Lifespan also tends to favor solid-state batteries, instead of the typical 1,000 to 1,500 full charge. Discharge cycles seen in lithium-ion batteries, solid-state batteries can deliver around 2,000 to 3,000 cycles, meaning their capacity fades more slowly over time. Charging speed is another key differentiator. Most lithium-ion battery systems go from 0 to 80% in about 25 to 35 minutes, while solid-state tech is targeting just 10 to 15 minutes, significantly cutting downtime. They also operate within a much broader temperature range, from -10 degrees Celsius to 50 degrees Celsius for lithium-ion, compared to from -20 degrees Celsius to 100 degrees Celsius for solid-state, which could simplify thermal management systems. Safety rounds out the list of advantages. By replacing flammable liquid electrolytes with solid materials, the risk of thermal runaway drops from moderate to high to virtually zero. That said, current lithium-ion chemistry still holds key strengths. It's proven, mass-produced, and highly cost-optimized. Top-tier lithium-ion cells are already pushing the upper limits of their energy density range, though results vary based on cell format and pack design. Some of the most impressive solid-state metrics come from controlled prototypes and transitioning those into mass production, while maintaining fast charge durability and addressing interfacial resistance, remains an active engineering challenge. For now, lithium-ion remains the practical choice for mainstream applications, especially where cost and supply chain maturity are critical. Still, the direction is clear. If manufacturers can industrialize solid-state batteries without compromising these numbers, they offer a compelling foundation for the next generation of electrified systems, with higher energy, faster charging, greater thermal resilience, and improved safety. When will semi-solid batteries hit the road in EVs? Lithium-ion batteries have long struggled with key challenges, including the risk of fire or explosion due to thermal runaway when damaged or overheated. On top of that, technological progress has been relatively slow, with energy density improving by just 5 to 10% per decade. Environmental concerns are also mounting, especially around the mining of raw materials like nickel and cobalt. Solid-state batteries offer major advantages, up to 2 to 3 times the energy density of today's LFP cells, along with impressive durability and superior safety. They're almost non-flammable. This is exactly why the EV industry often refers to them as the holy grail of electric vehicle batteries. Put simply, every battery cell is made up of 4 key components: a cathode, anode, electrolyte, and separator. As the name suggests, solid-state batteries replace these components, most importantly, the electrolyte, with solid materials. What truly sets them apart is the solid electrolyte layer positioned between the anode and cathode, whereas traditional lithium-ion batteries use a liquid electrolyte in that same space. This is where solid-state batteries shine. They can store more energy, deliver higher power output, and are significantly safer than their lithium-ion counterparts. Liquid electrolytes in conventional batteries are flammable, prone to leakage if the cell is cracked, and can trigger thermal runaway, a dangerous chain reaction that spreads from one cell to another. In contrast, most solid-state batteries today use ceramics or polymers as solid electrolytes. The application roadmap for solid-state batteries kicks off around 2025 and 2026, focusing on validating the technology under real-world conditions. Prototype cells are already being tested in trial vehicles by BMW, Volkswagen, and Toyota, while pilot production lines are up and running in the US, Solid Power, Germany, Ferasis, and China, Huawei. The current priority is stabilizing manufacturing processes, controlling key variables like separator thickness and moisture levels, especially for sulfide-based systems, standardizing cell formats, and conducting safety evaluations at the module and pack levels, all essential steps toward meeting regulatory certification standards. From 2026 to 2028, solid-state batteries are expected to enter a limited-scale semi-commercial phase, with a focus on premium segments and industrial storage, markets that can absorb higher costs in exchange for better energy density and safety. As cumulative production approaches 1 gigawatt-hour, prices are expected to begin stabilizing. Manufacturers will concentrate on increasing production yield, reducing defects, optimizing thermal propagation control, and fine-tuning battery management systems for lithium metal anodes using real-world performance data. Between 2028 and 2030, the goal is to scale up to mainstream vehicle segments, particularly compact sedans and crossovers, comparable to the Tesla Model 3 category, as solid-state battery costs approach parity with lithium-ion battery cells. At this stage, they must meet demanding requirements: long-cycle life warranties, minimal degradation under repeated fast charging, and full compatibility with 800-volt vehicle architectures. After 2030, the technology is expected to see widespread adoption across entire EV lineups and grid storage systems. This phase will go hand in hand with supply chain standardization, multi-source material strategies, the development of recycling protocols, and end-to-end cost optimization, all critical to ensuring large-scale reliability and sustainability. Back to BYD. The company has confirmed that its solid-state batteries deliver an energy density of 400 watt-hour per kilogram, nearly double that of conventional lithium-ion cells, which average around 210 watt-hour per kilogram, and significantly higher than BYD's current Blade battery, which offers about 160 to 165 watt-hour per kilogram. To achieve this performance, BYD has upgraded both the electrode materials and solid electrolyte. Reports indicate they use a synthesized oxide solid electrolyte combined with high-capacity anode and cathode materials to accelerate both charging and discharging speeds. These advancements also enhance ionic and electronic conductivity, boosting both energy density and overall battery efficiency. Imagine this. If you bought a current BYD Seal equipped with an 80 kilowatt-hour Blade battery, you'd get around 373 miles of range. Now, with the new solid-state battery of the same size, that range could jump to an astonishing 870 miles. But here's the thing. You might not even need that much capacity. A smaller 60 kilowatt-hour pack could still deliver up to 621 miles of range. That's insane. The higher energy density of solid-state batteries means you can store more power without adding weight, a critical advantage for electric vehicles. Of course, 400 watt-hours per kilogram isn't record-breaking compared to some other solid-state contenders. Companies like CATL, Amprius Technologies, and QuantumScape have already developed batteries exceeding 500 watt-hour per kilogram. But BYD is taking a more measured approach with its first-generation solid-state cells. Rather than chasing extreme specs too soon, they're aiming for a more attainable target, one that enables faster mass production and real-world rollout. From there, they can scale, and improve. Why aren't solid-state batteries used in EV right now? One of the most critical barriers is the scalable production of ultra-thin ceramic separators. These separators, placed between the battery's anode and cathode, are crucial for the flow of ions. Unlike the flexible polymer separators used in lithium-ion batteries, ceramic separators are rigid and fragile, making them prone to cracking during large-scale manufacturing. Producing them at commercial volumes with micron-level precision and mechanical durability has proven difficult. Many pilot production lines still suffer from high defect rates and unstable yields. Without a breakthrough in processing techniques and quality control, this component alone threatens to slow the rollout of solid-state cells. Another major obstacle is performance at low temperatures. Certain sulfide-based electrolytes, widely considered among the most promising candidates for solid-state designs, tend to lose significant ionic conductivity below 0 degrees Celsius. This degradation severely limits their functionality in colder climates, such as Europe, Canada, and the northern United States. For solid-state batteries to succeed globally, they must perform reliably in winter conditions. Achieving this will require new formulations or hybrid solutions that maintain conductivity without compromising stability or cost. Without progress here, many high-value markets will remain out of reach. Which solid electrolyte chemistry do you believe holds the most promise for commercial EV applications, and why? Please share your opinion in the comments section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. Gas-powered cars may still rule the roads for now, but make no mistake, their time is running out. Governments around the world are setting hard deadlines to eliminate them, and once those bans are fully enforced, it's over. And at the center of that revolution, Tesla. Whether you love them or hate them, there's no denying they've shaped the electric vehicle industry from the very beginning. But what's important is that Tesla isn't stopping. Based on everything we know, from leaks, interviews, investor calls, and internal reports, the Tesla Model 2 has finalized its design and is moving into mass production, set to hit the market by the end of this year. But let's be honest, it won't be an entirely new model like many had hoped. What it is, in truth, is a brilliant copy of the Model Y, infused with the best elements of the Model 3 and carrying subtle design echoes of the Tesla Cybertruck. What we get in return, however, is a $15,990 electric vehicle that still manages to understand your daily driving habits, and in the near future will even be capable of delivering itself to your doorstep autonomously. So, what exactly is the mass-produced Tesla Model 2 equipped with? Can an EV priced at $15,990 truly deliver real-world utility and reliability? Welcome to the Tesla Car World. Until now, Tesla's most ambitious and groundbreaking vehicle is no longer the Model Y, the Model 3, or any other familiar name you've heard before. We all know the Model Y is Tesla's most versatile vehicle to date, and it's also the company's most successful SUV. There's no question that Tesla owes much of its current standing to the Model Y. It's no accident that the Model Y became the world's best-selling electric vehicle and has held the top spot in the US and many other countries since its debut. Its price isn't exactly cheap, but it's not out of reach either, starting at $37,000 with federal tax credits. Still, the Model Y can't carry Tesla forever. Tesla's revenue and profits have taken a sharp hit at this year, and Elon Musk has only one clear path forward: launching the Model 2, the car that millions have been waiting for, because it's the only Tesla they can actually afford. Now let's set aside the obvious question: why hasn't Tesla launched it yet? Elon Musk has been talking about a $25,000 electric car since 2020, yet here we are, still waiting. The truth is, building an affordable EV is far more difficult than most people realize. And the biggest reason? Batteries. Batteries still make up the largest portion of an electric vehicle's cost, anywhere from 30% to 40% of the total price. And until recently, these batteries have relied almost entirely on lithium. Tesla has been using lithium iron phosphate and nickel manganese cobalt NMC chemistries for years. They're good, they're reliable, but they're also expensive. Lithium prices have surged and the supply chain is being stretched thin. Over the past year, Tesla has been quietly working on a brand new battery architecture, one designed not just to boost performance but to slash costs. The goal is no longer to build the best car money can buy. It's to build the best car that almost anyone can afford. We'll dive into what some are calling the insane new battery system powering the Model 2 later in this episode. But first, let's be clear. The Model 2 won't be some stripped-down, bare-bones Tesla, and it's definitely not a dressed-up golf cart. From everything we know so far, this will be a fully capable electric vehicle that shares the same DNA as the Model 3 and Model Y, just smaller, cheaper, and built for the masses. Think compact hatchback. Think urban maneuverability, the next-generation city car. When looking at Tesla's vehicle lineup, it's clear that Elon Musk has covered nearly every major category: sedan, crossover, pickup, and even heavy-duty trucks. But one thing stands out: they've been missing a hatchback. And the Model 2 is set to be the perfect addition to complete that collection. However, Tesla has opted for a smarter, more strategic approach because they understand the market and mainstream consumer preferences better than anyone else, thanks in large part to Elon Musk's vision and deep industry insight. That's right. Tesla will design the Model 2 as a crossover, specifically a subcompact crossover, significantly smaller than the Model Y. Initially, the Model 2 will be built at Giga, Texas, with a target production volume of up to 10,000 units per week, sharing the same production line as the Model Y. That means it will resemble a scaled-down Model Y, and Giga casting will play a crucial role in enabling the high-volume manufacturing of these vehicles. Tesla is famously tight-lipped about its upcoming products, and the next-generation vehicle is no exception. As of now, concrete details remain scarce, so aside from knowing it will be a compact crossover, we'll avoid diving deep into its exterior, since anything beyond that is pure speculation until Tesla makes it official. What we can do is analyze what's been confirmed by Tesla, trusted sources, and Elon Musk himself regarding the $25,000 EV. Musk has already stated that this new model will be built on an existing platform, which tells us a lot. It's clear the vehicle will still carry Tesla's signature design language, and as mentioned earlier, the Model 2 is shaping up to be a scaled-down version of the Model Y. Right now, the crossover segment is on fire, so releasing a smaller, more affordable version of the Model Y could be a massive win. That said, with the reduced footprint, expect scaled-down elements across the board, from the headlamps and front fascia to the hood line and rear quarters. Tesla will likely utilize more budget-friendly components than what's found in the Model Y to keep costs in check. But don't take that as a downgrade. Tesla's not in the business of building unattractive vehicles. Expect something that's fresh, minimal, and sporty, easily one of the most stylish EVs in its price class. The simplified design isn't a flaw. It's Tesla doubling down on making the $25,000 price tag a reality. Look closer, and you'll notice that Tesla's minimalist design approach isn't unique to the Model 2. It's a thread that runs through the entire lineup, even with premium models like the Model S and Model X, both of which avoid excessive complexity by design. And to be fair, most buyers don't seem overly concerned about the Model 2's looks anyway. What really matters to them is performance and price, which means that even if the design isn't groundbreaking, customers will still jump at the chance to own a Tesla for $25,000, because value outweighs styling. Interestingly, there have been multiple reports suggesting the Model 2 might arrive in two body styles, a hatchback and a crossover. We wouldn't rule this out. It would make a lot of sense from both a business and market perspective. While the crossover version has been internally confirmed by reliable sources, the hatchback rumor dates back to early leaks involving Tesla's budget EV program. One particular leaked prototype image with its short overhangs and compact frame strongly hinted at a hatchback design for tight urban settings. As we've noted, Tesla still doesn't have a hatchback in its current lineup, which makes this even more plausible, especially considering growing demand for hatchbacks in recent years. Hatchbacks generally come in at a lower cost than larger vehicles, and while crossovers dominate in the US, Hatchbacks are significantly more popular in markets like China and Europe. That's why so many Chinese EVs opt for this format today. If the dual-body rumor proves true, it wouldn't necessarily create production chaos. Both variants would likely share a large portion of their parts, reportedly around 80%, and would be built on the same underlying platform. Just as the Model 3 sedan and Model Y crossover share much of their production architecture, the Model 2 variants would follow the same philosophy. 2 styles, 1 system. Here's something else you may not know. The Model 2 is projected to be built at a scale far beyond the Model 3 or Model Y. Here's what Musk had to say on that.
We are working on a low-cost electric vehicle that will be made in very high volume. And I think the revolution in manufacturing that will be represented by that car will blow people's minds. It is not like any car production line that anyone's ever seen.
That's no exaggeration. Not only is Tesla aiming to produce millions of these over time, but internal reports confirmed earlier this year that the company is targeting production of 10,000 units per week. Manufacturing of the crossover version is expected to begin at Giga Texas, followed by expansion to facilities in China and Giga Berlin. When will the Tesla Model 2 reach the $15,990 price point? Here's the bottom line. Tesla is aiming to produce it for under $20,000. According to supply chain analysts and manufacturing experts, Tesla is targeting a production cost of $16,000 to $18,000 per unit for the Model 2. That would allow them to offer the car at a base price of around $25,000. So how is that even possible? Lithium manganese iron phosphate, or LMFP for short, has entered the scene. This isn't some sci-fi battery tech. LMFP has already been used by Chinese automakers like CATL and BYD. It's cheaper than traditional LFP, doesn't require expensive nickel or cobalt, and it's safer and thermally more stable. The only drawback? LMFP has traditionally had lower energy density, until now. But recent advancements have changed the game. Tesla and its partners are reportedly testing LMFP batteries with energy density on par with current LFP packs, while offering faster charging and longer lifespan. If these batteries are used in the Model 2, Tesla could cut battery costs by up to 30%. That's massive. But battery chemistry alone isn't enough. Tesla is also making a bold bet on structural battery packs. Instead of placing battery cells into modules and then installing them into a chassis, Tesla is turning the battery pack into the chassis itself. This eliminates redundancy, reduces weight, simplifies production, and increases structural rigidity. Simply put, it makes the car cheaper, lighter, and safer. Now, combine that with Tesla's ultra-fast gigacasting technology, where massive machines stamp entire underbody sections as a single piece, and you get a production process that's not just efficient, but revolutionary. Fewer parts, faster build times, lower costs. All of this makes the Model 2 not just possible, but inevitable. Right now, Giga Texas is primarily focused on building the Model Y and the Cybertruck, both of which take advantage of Tesla's groundbreaking gigacasting process. From what we've gathered, Tesla uses a 6,000-ton gigapress to form the front and rear sections of the Model Y, while the Cybertruck will require an even more powerful 9,000-ton press to handle its massive frame. The upcoming Model 2 is expected to adopt the same production approach as the Model Y. Thanks to the efficiency and cost reductions enabled by gigacasting, we're confident that the Model 2 will be built using this advanced method. It's one of the key enablers that makes the $25,000 price tag more than just a promise. In fact, without gigacasting, hitting that price point might not even be possible. Even though Tesla's gigapress and gigacasting technologies have gained a lot of attention over the years, not everyone fully grasps what they are or why they matter so much to EV manufacturing. So let's break it down briefly and explain why this tech is such a big deal. In the past, Tesla, like most traditional automakers, assembled the lower frame of vehicles such as the Model 3 by welding together numerous individual components. But everything changed when Elon Musk had a light bulb moment, sparked by none other than a Hot Wheels toy car. He envisioned a radically different approach. What if Tesla could cast a large section, or even most, of a vehicle's body in one go? That vision gave rise to the idea of the Giga Press. a giant casting machine developed and delivered by Italian manufacturer IDRA, which would go on to revolutionize Tesla's production process. Last year, when rumors about the production of Model 2 spread, Reuters reported that Tesla had ambitious plans for the Model 2, aiming to produce up to 10,000 cars per week, equivalent to 500,000 cars per year. This seems credible because Elon Musk previously stated that this would be a car produced in extremely large quantities. Notably, Tesla has confirmed that the next-generation model is now deep in pilot production and will be assembled on existing production lines with minimal modifications, allowing for faster production and optimized costs. If all of this comes true, and signs point to it already happening, the Model 2 could be a major turning point in making electric vehicles more accessible, offering an affordable car while still retaining Tesla's signature DNA. Based on our analysis of Tesla's current factories, the Model 2 is now most likely being produced first in Giga Shanghai, which continues to lead Tesla's global output and efficiency. The factory, which can now produce a Model Y in under 40 seconds, has one of the most optimized production lines in the world. Asia and Europe remain Tesla's most crucial markets, featuring flexible supply chains and competitive production costs. With pilot builds of Model 2 reportedly underway since mid-2025, full-scale ramp-up is expected imminently. Once Tesla establishes a stable production process, expansion to the U.S. could follow, with the Fremont factory in California being the top candidate. However, the possibility of production at Gigafactory Berlin remains uncertain. While Europe is a highly promising market, significantly higher labor costs could reduce the Model 2's price advantage, making production in Germany less attractive compared to China or the U.S. If Tesla truly aims to keep the starting price around $25,000 to $30,000, the company will need to carefully evaluate its manufacturing locations to optimize costs without compromising quality or production volume. In reality, Tesla still has several ways to achieve low costs with the Model 2. What do you think about the company deploying Optimus robots in the car's production line? This idea isn't far-fetched considering Elon Musk revealed in early 2025 that over 1,000 Tesla bots would be working in factories by the end of the year, and according to the latest shareholder update, several hundred Optimus units are already performing basic tasks in Giga Texas and Giga Shanghai. Deploying Optimus robots into the Model 2 production line is not only feasible, but could be a game-changer for the automotive industry. Elon Musk has repeatedly emphasized his ambition to automate manufacturing with humanoid robots. And if Tesla successfully integrates thousands of Optimus units into its factories this year, the Model 2 could be the first car to benefit from this innovation. With the ability to work continuously, without breaks or wages, Optimus could significantly reduce labor costs, one of the key factors affecting vehicle pricing. Additionally, if Tesla uses Optimus to replace human workers in labor-intensive yet simple assembly tasks, the company could reallocate employees to more critical roles, optimizing efficiency and accelerating production speed. This is especially crucial for an affordable model like the Model 2, where Tesla is targeting large-scale production at a price of around $30,000. With the Model 2, Optimus could be deployed in assembly, quality control, and even production optimization. Imagine a factory where humanoid robots work alongside humans, performing precision tasks such as tightening bolts, inspecting internal components, or monitoring paint quality. Thanks to their ability to learn and adjust movements dynamically, Optimus robots could handle repetitive tasks with higher accuracy, minimizing errors and boosting production speed. We don't have to wait much longer. The future of Optimus is just around the corner. It's incredible to think that only a few years ago, humanoid robots seemed like a distant dream. Yet Tesla is now on the verge of making the impossible a reality. With a production cost of just under $10,000, Optimus isn't just a revolutionary product. It has the potential to become the biggest tech breakthrough in history. And the craziest part? Elon Musk has just confirmed plans to scale production up to 500,000 to 1 million units annually by 2026. With Tesla replacing human workers with Optimus robots in the Model 2 production line, is this a giant leap for mankind or the beginning of mass job loss? Please share your opinion in the comments section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video. Goodbye.